Quantum control is at the core of quantum computing. A qubit pulse is a brief controlled energy pulse used to manipulate a qubit's quantum state. You can think of a transmon qubit as an ultra cold circuit that is cold enough to serve as a perfect quantum system. In this sense, you may think controlling it is like a flipping a switch. The truth is, controlling a qubit is extremely delicate. We can generate very precisely timed bursts of microwave energy that are small pulses in times that correspond to the steering wheel and accelerator in the car. The timing of these pulses forwards and reverses the qubit from one state to another, like 0 to 1 or superposition. However, if the pulses are not shaped correctly or have too short or too long misstep time, the entire system could drift with errors over time. This is why pulse level control is so much more important than just running a quantum algorithm. We want every single gates or operations to be accurate and precise. The most important quantum technologies are superconducting qubits like the transmon. Unlike traditional qubits, which are constructed using material properties of an atom, superconducting qubits are effectively realized with superconducting circuits that will behave like artificial atoms with discrete energy levels. We then drive the transitions of these levels using microwave pulses. While that comparison will only go so far, you could think of this like tuning a musical instrument. More than capturing the physical qubits like gates X, Y, and Z, by carefully shaping and calibrating of the chosen pulses, we could implement any gate.
Qiskit Pulse, a pulse-level programming model for quantum hardware. It implements the open pulse specification to control quantum operations using low-level instructions. Most users operate at the circuit level, that's Qiskit era. But for precise control, like calibrating a gate or correcting crosstalk, we move to pulse level. This lets us control the timing, amplitude, phase, and the shape of each pulse. It's essential for error mitigation and gate optimization, like designing a custom gate, and finally, these are run on hardware via Qiskit runtime. Key instructions include a schedule. A time-ordered sequence defines exactly what happens on each channel and when for precise quantum experiments. Play used to get the output waveform. Delay, set frequency, shift phase specify the shape of the waveform, timing, and even customized measurement schedules. Key channels are drive channel, control channel, and measure channel are used to interact with the qubits. Acquire is used to collect results. Common pulse shapes include Gaussian, track, constant, Gaussian square, and arbitrary waveform. Track pulse modifies the Gaussian pulse by adding a derivative term beta to reduce leakage to high energy states by shaping both the real and imaginary quadratures of the control signal. Parameters like amplitude and sigma define the height and the width of the pulse and are tunable in code. These are mixed with high frequency carriers by waveform generators. Look at the difference between the circuit and the pulse model in quantum computing. At the circuit level, we use logic gates to build algorithms. Here we can't access the details of how measurement happens or tune if it's noisy. Qiskit Pulse goes beneath the circuit abstraction and directly programs the control pulses. This matters in Rabi experiment where pulse level amplitudes determines the gate calibration. With pulse level access, we can adjust parameters directly and gain full visibility into the system's physical behavior.
In this project, we explore the design of a custom X-gate using drag pulses with IBM Qiskit Pulse. We start by importing the required packages and simulating on the Fakeamonk backend. Then we assume some initial parameters for the drag equation and create the drag pulse and schedule this pulse. Next, we build the custom X-gate and map it to a quantum instruction using instruction schedule map. Further, run the job to get the result of counts respectively. Upon applying to an initial zero state, our pulse performs a rotation, resulting in a final probability of one state equal to 68.94%. For comparison, we also test IBM's ideal built-in X-gate to evaluate the effectiveness of our custom design. This code demonstrates the potential of pulse-level control in optimizing quantum gates for real hardware.
After initial design, we wanted to get better results, and we decided to run a Rabi experiment and an optimization technique to see what amplitudes worked best. With the qubit initialized at 0, we swept the amplitude of the drag, the derivative removal by adiabatic gate pulse, and plotted the probability of measuring the 1 state. We found that this was some sinusoidal function, which makes sense in the context of Rabi oscillation. From this, we found out what the pi pulse amplitude was, finding the minimum amplitude needed to rotate the qubit from 0 to the 1 state. This guess resulted in something close to 0.995 for our initial amplitude, and this was the starting point of our pulse calibration. Variational pulse learning came after this, where we used the Bayesian optimization. Bayesian optimization is an ML technique that models a cost function using probability to choose the best next parameters. With 2 parameters, amplitude and beta, we used this technique to run 50 iterations and a new drag pulse was made. We used this part in our instruction set when it was then tested. The cost function we used was p equals 1 minus the counts of 1, which is just the amount of 0 counts. Then we minimized p, maximizing the probability of ending up in the 1 state. This leads to the histogram where the 1 has about 815 counts and the 0 has 209. The ideal count would be closer to 965 and 59. We chose Bayesian due to how efficient it was and by looking at numerous papers about it in this context. It gave us optimized results for beta and amplitude, but our amplitude value was very similar to what the Rabi experiment already gave us. With this, the histogram became slightly closer to the ideal case.
So, we have now extended our project to real-time pulse adaptation for error mitigation. To evaluate the robustness of our custom X-gate, we intentionally introduced errors by simulating drift in the control parameters. These drifting values mimic real-world hardware noise and instabilities. Using these drifted values, we then rebuilt the drag pulse to observe its performance under degraded conditions. Next, we applied real-time pulse adaptation using the adaptive gradient algorithm. This technique iteratively adjusts the pulse parameters to counteract the drift. Here we can observe that the pulse is adapting to the simulated drifts for each iteration. With the final adapted parameters from AGA, we generated a new drag pulse and reconstructed the custom X-gate. After optimization, we observed significantly improved results with better fidelity in the X-gate execution when compared to all of our previous simulations. This version was better tuned for the current quantum environment, effectively mitigating the effects of drift, and we can also implement this using real quantum hardware with better optimization techniques for even better results. Thank you.